Okay, guys, we are going to talk about extending our idea of using f prime to figure out about the shape of graphs. Today we're going to talk about local extrema. And I have two definitions and two theorems for you today. The first definition is a review from yesterday. The definition is, we're going to say that x equals c is a critical point of f of x. If 1 f prime of c is equal to 0, that would be a horizontal tangent. Or 2, f prime of c does not exist. And that would occur at a corner, vertical tangent, or cusp. Mostly. There are other ways for f prime of c to not exist, but those are the popular ones. Yes? That is definition for critical point. And so what you guys did in your homework last night was to find critical points of f, and then you use those critical points to construct number lines for f prime, identify intervals where f prime is positive or negative, and conclude that f prime is increasing on the intervals where f prime is positive and decreasing on the intervals where f prime is negative. So this is all very familiar. Now what we're going to do is to talk about a second idea. We're going to say that f of c is a local maximum if f of c is greater than or equal to f of x for all x in some open interval. Now let's unpack this definition so that we can understand what this means. And here, Jason, we are defining the local maximum. The way to read definitions is to look for the is a. F of c is a local maximum if blah, blah, blah. So let's draw a picture of what we're talking about here, and I want to consider this f of x right here. And I want you to notice that the largest points of f of x that we can see on its domain are points over here, right? These points right here. But right here at this point, it is the case that this f of c is the largest in its neighborhood. I can draw an open interval a to b around c so that within just this little local neighborhood right here, f of c is the largest value. To use a sports analogy, this is like being best in your league, right? There can only be one best free throw shooter of all time, but there can be lots of different best free throw shooters in your league. The best free throw shooter of all time, that's a global maximum points scored free throw shooter. The best free throw shooter in the league is a local maximum best most points scored free point shooter, because it is relative to that neighborhood. Does that make sense to everybody? So, what do you notice about the value of f prime at this local max? 0. Yeah. Excuse me. It is 0, and that is not actually an accident. You can see why that has to be, because if f increases to this point, and then f of c is a max, then f must decrease thereafter, which means that f prime has to change signs, which means I either have to have a horizontal tangent or fail to exist. So there's our definition. Now, likewise, we're going to say that f of c is a local minimum. So here we have a local minimum if f of c is less than or equal to f of x for all x in some open interval. And in particular, you can see that this point right here, let's call this D. And this value would be f of D. F of D is a local minimum because it is the smallest value in its neighborhood. And observe also that f prime of D is equal to 0. We've got a horizontal tangency right there as well. How are we doing so far? Do these definitions make sense? Taken together, the local maximum and local minimum are called local extrema. So a local extrema is just a way to describe local maxes and mins. And it's the plural of extremum or extreme value. The extremes of something are the edges. Yes, that's right. The local extrema could be local maxes or local mins. Okay? Now, with these two definitions in place, critical point, f prime equals 0, or f prime does not exist, and local max, local min, the max, the min in their neighborhoods, we are going to have two theorems. What we'd like to be able to do is to find local maxes and mins because that will answer a question for us. And our question when we were drawing functions last night is, I know I'm going up when f is increasing, but how far up do I go? And the answer to that question is, if I know where the local max is, I can go up to the local max and stop. And then come back down to a local min and stop, and etc. So we want local maxes and mins because they tell us how far up and down to go on our curves. How do we find them? Well, we're going to have two theorems. And the first identifies for us candidates for local maxes and mins. And that is Fermat's theorem. And Fermat's theorem is easiest to state like this. Local extrema only occur at critical points. Local extrema only occur at critical points. Now, as with our other theorems, I'm not going to prove them at this time. I will in January, but I want to make this plausible to you. If I have a function that maybe has a local maximum right here at C and a local minimum right here at D, you can see that what has to happen is that if my function's name is f, my number line for f prime has got to show that f goes from increasing to decreasing. And the only way that can happen is if f prime either becomes 0 or else does not exist, as in over in D right here. So there are only two ways that you can change sign. One is to go through 0, and the other is to simply jump there. Does that make sense? So if I were to look at a graph of f prime, you remember graphing f prime? Our graph of f prime would look like this. F prime is positive until C, and then it's 0 at C, and then it's negative, and then right at D, it experiences a jump discontinuity and becomes positive like that. Corner, actually, show corner. It would be a cusp if our derivative became infinite. Negative infinity one side, positive infinity the other. So this is f prime right here, and you can see from the number line, and you can also see from the graph of f that f prime should look like this. Does that make sense? Now here's what this does for us. What Fermat's theorem does for us is it allows us to identify candidates for our local maxes and mins. In other words, the candidates, the possible local maxes and mins, are going to be those places where f prime is equal to 0 or f prime does not exist. In other words, at critical points of f. So our basic procedure for identifying those candidates is going to be to find f prime, set it equal to 0, or find the values for which f prime does not exist, and these, the solutions to these, become the candidates for our local maxes and mins. And we can see those candidates directly on the f prime number line. These here are the candidates identified by Fermat's theorem as possible local maxes and mins. Having identified those candidates, though, we now ask the question, well, are they local maxes? Or are they local mins? Or maybe they might be neither. So how do we find out? We're going to find out by a second theorem, a test for the candidates that uses the first derivative. And so we call this the first derivative test. The purpose of the first derivative test is to take those candidates and identify them positively as either a local max, or a local min, or neither. And it goes like this. If f prime changes sign from plus to minus at x equals c, then f of c is a local max. And the picture that we want to have is of a function that looks just like this. If this is the graph of f, you can see that f prime of c right here is 0, so that is a candidate for being a local max. And you can also see that the number line for f prime looks just like this, positive then negative. And so if I look at the f prime number line, I can see that at x equals c, I am changing signs from positive over here to negative over here. And as a result, I can look at that sign change and immediately conclude that f of c is a local max. And the only information I need to conclude that is just the number line. Likewise, if f prime changes sign from negative to positive at x equals c, then f of c is a local min. And here we can have a graph that looks like this. And I deliberately created a graph here where f prime of, let's call this g, since It's a different function from our f right there. I deliberately created a graph right here where g prime of c does not exist. Doesn't matter whether my critical point is of the first type, where f prime of c is equal to 0, or of the second type, where g prime of c is non-existent. I can still apply the first D test and see that because g prime changes sign from negative to positive, therefore g of c is a local min. And the language we would use to describe that is the language that is borrowed directly from the first D test. So if I were analyzing this function g right here, then what I would say, based on the information from the number line, is that g of c is a local min because, and now I borrow the language directly from the theorem, because g prime changes signs from minus to plus at x equals c. And this justifying language comes straight from our. Well, are there any other possibilities besides changing sign from plus to minus or changing signs from minus to plus? You say yes. What other possibilities could there be?
The sign doesn't have to change.
That's right. The other possibility is my sign doesn't change. It could be positive on both sides of the critical point or negative on both sides of the critical point. An example of such a function could be something like f of x equals x cubed. And when I do a well-labeled number line for that, I can see that I have a single critical point at 0, and the derivative is positive on both sides. What does that mean? That means that my curve is going to have a horizontal tangent right here, as it's going to go up to a horizontal point of horizontal tangency and then go up some more. Later on, we're going to call that a shelf point. For the purposes of our first D test is we're going to say otherwise, if not a sign change, if no sign change, then f of c is neither local max nor local min. So we have three possible outcomes. Sign change from plus to minus, local max. Sign change from minus to plus, local min. Neither one, then neither one. I'll see you guys on Monday. Have a